In this slidecast, I'll take you through all of the answers to the chemical analysis workshop. First of all, we'll start with question 1. Now, question 1 relates solely to the infrared spectroscopy content. Now, this question asks you to describe the steps that are required to prepare a KBr disc containing phenylephrine, which is this compound here, and that this should be suitable for infrared analysis. Now, this will require you to review the content from week 7, in which we discuss the various ways of preparing a sample for infrared analysis. Now, if you look at that content, you'll see that for a KBr disc, you will first need to grind the sample with potassium bromide. And for this answer, you need to give an indication of the quantities required. So 10 to 20 milligrams of sample and 100 to 150 milligrams of potassium bromide. These are ground together and then you compress these into a disc. I would not expect you to put in additional details such as requiring a 10-ton press or needing to add your sample to a die before it is compressed. You would just need to mention the key stages. So you would need to say the sample is ground with KBr, give an indication as to the quantities required, and compress into the disc. This question will be a 3-mark question and there will be 1 mark for each of those components. Question 1b requires you to know not only what the KBr disc method involves, but also about the New-Joel-Mull method and why this method will give you a slightly different infrared spectrum to using KBr. Now, the question says that the infrared spectrum of compound 1, which is here, differs significantly from the reference spectrum, which was acquired by preparing a New-Joel-Mull, and it asks you to account for this observation. Well, New-Joel is an oil. It's an aliphatic oil containing carbon-carbon and carbon-hydrogen bonds. Now, in the New-Joel-Mull method, you must mix your sample and grind it with this oil. So the spectrum that you see is a combination of the spectrum from the oil and the spectrum from the sample. In contrast, using the KBr method, the potassium bromide is invisible to infrared light. It doesn't absorb it. And therefore the infrared spectrum that you get comes solely from the sample. So the answer to this question is that New-Joel is liquid paraffin, or you can say it's an oil, and therefore absorbs infrared light. The biggest differences are around the CH absorption regions. These are typically around 2,900 wave numbers, but anything between 2,900 and 3,000 wave numbers would be accepted, and in the fingerprint region at 1,450 wave numbers. So you would expect to see peaks in the infrared spectrum at these absorbances. And so that is the key factor that would cause a New-Joel-Mull sample to have a different infrared spectrum to one prepared with a potassium bromide disc. Now, question 1c asks you to compare what you would expect in the infrared spectra for these two compounds. So we have compound 1, which is a precursor to phenylephrine, which is compound 2. Now, the way that you should approach this question is you should first start by looking for what differences there are between the two molecules. This will allow you to identify changes in functional groups, which you can then link back to the anticipated changes in the infrared spectrum. Now, in these molecules, if we have a look at where the differences are, they lie on the left-hand side. So when going from compound 1 to compound 2, we lose this carbon double bonded oxygen, so this carbonyl group, and we gain an OH group. So when we go from 1 to 2, we lose a carbonyl group and we gain an additional OH or alcohol group. And so the answer to the question that I would expect is for you to state that there is a loss of carbonyl signal between 1550 to 1750 wave numbers, and this would be the key difference. So there would be no carbonyl signal in compound 2, but there would in compound 1. I would also expect you to say that the OH absorbance between 3000 and 3600 wave numbers would also increase. However, if instead of asking you for all the differences between the spectra, I asked you for one key indicative difference that would tell you that you had made compound 2 from compound 1, you would have to go with the loss of the carbon R signal. An increase in OH absorption on its own doesn't guarantee that you solely have compound 2. The only thing that can do this is the loss of the carbon R signal. Now, other factors can also cause an increase in absorbance of the alcohol group, such as the presence of solvent containing an alcohol, or if you added additional sample into the infrared spectrophotometer. So the alcohol group change on its own would not guarantee that you had made compound 2 from compound 1. For that, you would need to lose the C double bond O absorption from this group here. So let's look at question 2A and 2B together. Now these questions ask you to define A 1% 1cm, C and L from the Beer-Lambert law, and then give the units for 3 of these terms, so the A 1% 1cm, C and L. Now this was covered in the lecture material and requires you to know what each of these terms are and how they are defined and what their units are. So A is the absorbance of sample. So this is the measured absorption that we would have. A 1% 1cm is a specific absorption coefficient, and this is a value that you would look up. It is the value that is a absorbance of a 1 weight percent solution in a 1 centimetre path length. And so this is the value that can be found in sources such as the British Pharmacopoeia. L is the path length, and you can always assume that this is 1 unless you're told otherwise. And C is concentration. Now the units for these 3 terms are deciliters per gram per centimetre for the specific absorption coefficient, centimetres per path length, and you can always assume these are 1 unless you were told otherwise, and grams per deciliter or grams per 100 ml for concentration. You can use either of these terms and they are completely interchangeable. So let's look at question 2C. Now question 2C requires you to work out what the units are for absorption from your answer for parts A and B. And so I've put the answer to parts A and B here for easy reference. Now the way that we do this is we take our Beer-Lambert law equation and we substitute in the units for each component within the equation. So we start by writing out the equation, and then we put the units from each of these terms into that equation. And you can see these here. Now it turns out that these units all cancel out with each other. So deciliters per gram cancels out grams per deciliter, and per centimetre cancels out with centimetre. So what this means is that A is a unitless quantity. It has no units associated with it. Now, if you are looking in textbooks or in papers, you might see a unit referred to as ABS. This simply means absorption units. There are no formal units associated with absorption. Okay, so this last question was actually an exam question from 2 years ago. So I wanted to show this to you so you could see the format of an exam style question. Now, the first thing that you need to do to approach this question is to read it very carefully and make sure that you highlight all of the important information. This will then help you when you need to take numbers to put into the Beer-Lambert law later on in answering the question, and will also help you to understand the process by which the absorption reading was obtained. This will then help you to calculate the right amount of paracetamol that was in the original tablet. So we're going to go slowly through the text in the question and pull out some of the key information. Now, first of all, you're told that a student dissolves a paracetamol tablet in 100 ml of phosphate buffer at pH 8. Now, the important part of this sentence is that they dissolve the paracetamol tablet in 100 ml. Now, because this question will ask you to determine the amount of paracetamol in the original tablet, this question is about concentration, and it's about using the Beer-Lambert law. So this means that having the tablet dissolved in 100 ml is very important, but the identity of the buffer and the pH of the experiment is not. These are given because it is best practice to always quote the conditions under which an experiment was conducted. However, that doesn't mean that all of the information that is given is relevant to you. Now, the resulting solution is diluted by a factor of 1,000 to permit measurement by UV visible absorption spectroscopy. Now, the important part here is the dilution. So we know that the concentrated solution containing the tablet has been diluted by a factor of 1,000 to enable it to be measured using UV visible spectroscopy. That means that any numbers that you get in the rest of the question are likely to be from this dilute solution, not the original concentrated one. And that means that at some point we're going to have to work backwards to the concentrated solution from the dilute solution. You're then told the student obtains an absorbance reading of 0.3575 at 257 nanometers. The key piece of information here is the absorbance value. This is the A term in the Beer-Lambert law, and so we have our first number that will be used to plug into the Beer-Lambert law. Now, you're also given the wavelength at which this number was obtained. Now, this wavelength is not important to you, and you do not need it to answer any of this question. So please do not try and use the wavelength in the Beer-Lambert law. You're then told that the specific absorption, A 1% 1cm for paracetamol, is 715. And so this is your next term in the Beer-Lambert law, the A 1% 1cm term. Now again, you're given the wavelength, and so you can ignore this wavelength. It's not used at all. And then you're asked to calculate the amount of paracetamol in the original tablet. You're told to show all your workings, which is very important because if your workings are correct but your final answer isn't, we can often give partial credit for your answer. So if you show all your workings, you may be able to score a couple of marks. You're told to use the Beer-Lambert law, and you're given the Beer-Lambert law, which means there will be no marks for writing down the equation. You're told to use a path length of 1 centimetre, which gives you your last term to plug in to the Beer-Lambert law. So we've got the A 1% 1cm, and the L term, and we're going to be trying to determine C. So that's all the numbers that we need for the Beer-Lambert law. And crucially, you're told to give your final answer in milligrams. That means if you are giving your final answer as a concentration in grams per 100 ml, then your answer is going to be incorrect. The final answer should be an absolute amount in milligrams. So first of all, we write out the Beer-Lambert law. Now the reason for this is it gets you into the right frame of mind to answer the question, and we can start to see where we can plug in numbers into this equation. So the next step is to plug the numbers in that you have been given in the question. And just to note again, the wavelength is not needed. So if we take the numbers from the question, we have our absorbance reading of 0.3575, our specific absorption of 715, and our path length of 1. And we get the equation like this. Now the next step is to rearrange the equation to make C the subject. And to do this, we need to divide both sides by 715 times by 1. And when we do this, we get this equation. So 0.3575 divided by 715 times by 1 is equal to the concentration. Now if we solve this, we get a value of 0.0005 grams per deciliter, or grams per 100 ml. However, this value is for the dilute solution. Now the solution was originally diluted by a factor of 1,000, so essentially the concentration was divided by a factor of 1,000. So to get back to the concentrated solution, we need to multiply by 1,000. So it means that we need to take this value here and multiply this by 1,000 to correct for the dilution. This will then give you a value of 0.5 grams per deciliter. However, this is not the amount that is in the original tablet. We need to convert this into a mass, and we can do this by looking at how much solution we originally had. So the tablet was originally dissolved in 1 deciliter or 100 ml of solution. As we have a solution that has a concentration of 0.5 grams per 100 ml or per deciliter, this means that the amount dissolved in the solution is 0.5 grams, and therefore the amount of paracetamol in our tablet was 0.5 grams. However, you've been asked to give your answer in milligrams, and therefore you need to do a final conversion. So you convert from grams to milligrams by multiplying by 1,000. And you'll get that you have 500 milligrams in the original tablet. Now, if you have any questions about the questions and answers that I presented to you here in the slide cast, please feel free to post on the support forum.